So, we defined heat capacity, specific heat capacity and molar specific heat capacity. In molar specific heat capacity, what is molar specific heat capacity? It is the amount of heat required to raise the temperature of 1 mole of gas by 1 degree Celsius. In this molar specific heat capacity, we have molar specific heat capacity at constant volume and molar specific heat capacity at constant pressure. That is nothing but CV and CP. Molar specific heat capacity is denoted by the symbol C. Molar specific heat at constant volume. If the volume of the system is fixed and the pressure inside the system changes, then we call that as molar specific heat at constant volume. If pressure in the system is fixed and the volume changes, volume of the system changes, then we define that molar specific heat capacity as molar specific heat capacity at constant pressure. Let us see one example. Consider a pressure cooker. So, there is a cooker. So, we are supplying heat energy to the system. So, this is a system. Inside the system we have gas molecules. Here volume is fixed. Here we are using a pressure cooker. So, volume of the system is fixed. The volume will not change. We are heating this system. What happens? When we heat the system, molecules, gas molecules inside the system absorb energy. They start to move. Their velocity increases. Their kinetic energy changes. Kinetic energy is nothing but the internal energy. So, internal energy of the system changes. What happens to the pressure? We know that if the volume is fixed, then the pressure inside the system increases. Pressure inside the system increases because we are supplying heat energy. Volume of the system remains constant. So, we have to increase the temperature by 1 degree Celsius. For that, to increase the temperature of the system by 1 degree Celsius, we are supplying certain amount of heat. Pressure of the system changes. So, in molar specific heat capacity, we say that it is the amount of heat required, to change the temperature of 1 mole of gas. Here we are taking 1 mole of gas by 1 degree Celsius at constant volume. So, here the volume is fixed, pressure is changing. The gas molecules are heated up, therefore, pressure changes, temperature raises by 1 degree Celsius. So, this is CV, molar specific heat capacity at constant volume. Now, what is CP? It is nothing but the molar specific heat capacity at constant pressure. For that, what we have to do? We have to consider a system with the movable piston, because in this case the volume is not fixed. Volume changes, what remains constant? Pressure remains constant. For that, we are taking a system in which we have a piston, and this piston is movable. Inside the system we have gas molecules. We are supplying heat energy. So, what happens to pressure and what happens to volume of the system? When we supply heat energy, the molecules inside the system absorb the energy, their speed increases, their energy increases. So, as a result, these molecules apply force on the piston. When they apply force on the piston, this piston moves in the upward direction. There is displacement of the piston. As the piston displaces from its original position, volume of the system changes. So, the piston comes here. So, this is the original volume and this is the new volume of the system. What we observe here is volume of the system changes, but the pressure inside the system remains constant. Temperature rises by 1 degree Celsius. Temperature rises by 1 degree Celsius, volume changes, but what remains constant? Pressure remains constant. So, this is nothing but molar specific heat capacity at constant pressure. It is the amount of heat required to raise the temperature of 1 mole of gas by 1 degree Celsius at constant pressure. Here the gas molecules heated up and they apply force on the piston. So, work is done by the gas molecule. Here the gas molecules are heated, there will not be any work done because the volume of the system remains constant. But here the work is done by the gas molecules in case of Cp. So, this is Cv, this is the definition of molar specific heat capacity at constant volume and molar specific heat capacity at constant pressure. Now, there is a relation between this Cp and Cv. What is that relation? How they are related? Cp and Cv. We have to find out the relation between molar specific heat capacity at constant volume and molar specific heat capacity at constant pressure. For that, consider or in first law of thermodynamics. In first law of thermodynamics, we have delta Q is equal to delta U plus delta W. That means heat energy absorbed by the system is used to increase the internal energy of the molecules and work done. So, work done by the system. So, this is what first law of thermodynamics states. Here we are considering 1 mole of gas. For 1 mole of gas, if the gas is ideal gas, you just imagine that the gas is ideal gas and the gas obeys Boyle's law as well as Charles' law. The gas which obeys Boyle's law and Charles' law, we call that gas as ideal gas. So, Cp is equal to, what is the expression for, or what is the expression for molar specific heat capacity? The general expression for molar specific heat capacity is C is equal to 1 by mu into delta Q by delta T. How we got this expression? If we have mu moles of gas, amount of heat required to raise the temperature of mu moles of gas by 1 degree Celsius is nothing but its heat capacity, right? Amount of heat required to raise the temperature of mu moles of gas by 1 degree Celsius is its heat capacity, and heat capacity is denoted by delta Q by delta T. Amount of heat required to raise the temperature of 1 mole of gas, here mu is 1, mu means the number of moles in a gas. For 1 mole of gas, the amount of heat required is molar specific heat, C. On cross multiplication we get C into mu is equal to delta Q by delta T into 1. So, C is equal to 1 by mu into delta Q divided by delta T. This is the general expression for molar specific heat capacity. If mu is equal to 1, for 1 mole of gas, mu is equal to 1. In that case, C is equal to delta Q divided by delta T. C is equal to delta Q divided by delta T. So, at constant volume, CV, this is the general expression, CV is equal to 1 by mu delta Q divided by delta T. Similarly, for CP is equal to 1 by mu into delta Q divided by delta T. What is the SI unit of molar specific heat capacity? Heat energy is measured in joules, mu, moles, temperature, Kelvin. Joule per mole per Kelvin is a SI unit of molar specific heat capacity. Okay. Here what is delta Q? Delta Q is the heat absorbed by the system. Heat absorbed by the system. What is delta U? Delta U is the change in internal energy or increase in internal energy of the molecules, internal energy of the system. Delta W is the work done. Let us divide this equation by delta T. Let us see what happens. Delta Q divided by delta T. Delta T means change in temperature. The temperature changes by 1 degree Celsius. So, delta T is change in temperature is equal to delta U by delta T. We are dividing both sides by delta T plus delta W divided by delta T. Delta Q by delta T is equal to delta U by delta T plus delta W divided by delta T. We know that delta W is equal to P into delta V. So, delta Q by delta T is equal to delta U by delta T plus P into delta V. Delta W is nothing but P into delta V divided by delta T. Now, consider a process where volume of the system is fixed. That is, we are talking about the molar specific heat capacity at constant volume. If the volume of the system is fixed, then V is constant. Volume of the system remains constant. Then what is the change in volume of the system? Always change is represented by delta. So, change in volume delta V is equal to, how to calculate the change? Delta V is equal to final volume minus initial volume. Final value minus initial value is nothing but the change in the value. So, delta V is equal to final volume. We know that volume of the system is constant. So, the final volume and the initial volume both are same. So the change in volume delta V is equal to 0. There is no change in volume of the system because the volume of the system is fixed or it is constant. So the change in volume delta V is equal to 0 because the final volume and the initial volume remains the same. Final minus initial is equal to 0. So change in volume is equal to 0. Delta V is equal to 0. Now this expression becomes delta Q by delta T is equal to delta U by delta T plus P into delta V is 0. 0 into P is nothing but 0. So the second term becomes 0. Delta Q by delta T is equal to delta U divided by delta T. Here I write V. Suffix V indicates that the volume is fixed or V is constant. Delta Q by delta T. What is delta Q by delta T? We know that molar specific heat capacity at constant volume Cv is equal to, what is the expression for Cv? 1 by mu delta Q divided by delta T. Here we are taking 1 mole of gas, so mu is equal to 1. So Cv is equal to delta Q divided by delta T. So in this expression delta Q by delta T is nothing but Cv. So instead of delta Q by delta T, we can write Cv. So Cv is equal to delta U divided by delta T at constant volume. Cv is equal to delta U divided by delta T. No need to write V here because the internal energy is independent of volume. It depends only on the temperature, so no need to write suffix V here. So Cv is equal to delta U divided by delta T. Now consider the second process, that is at constant pressure. At constant pressure, that is P is constant, we have the equation delta Q by delta T is equal to delta U by delta T plus P delta V divided by delta T. Pressure is constant, so P is constant, so this expression remains the same. In the earlier expression, V is constant, so delta V is 0, this whole term is equal to 0. But now we have P constant, so there is no change in this expression, so the expression remains the same. Delta Q by delta T is equal to delta U by delta T plus P into delta V divided by delta T at constant pressure. So P. Suffix P indicates that the process is happening under constant pressure. So P. Delta U by delta T. So delta Q by delta T at constant pressure is nothing but Cp, molar specific heat at constant pressure. Cp is equal to 1 by mu into delta Q by delta T. Mu is 1, so Cp is equal to delta Q by delta T. So instead of delta Q by delta T, we write Cp. This delta U by delta T at constant pressure delta U by delta T. It is enough if you write delta U by delta T. No need to write suffix P here because internal energy is independent of P. So, delta U by delta T is equal to what? CV. So, Cp is equal to Cv plus Cp is equal to Cv plus P into delta V by delta T at constant pressure. At constant pressure. For 1 mole of an ideal gas, we have the ideal gas equation PV is equal to mu RT. The ideal gas equation is PV is equal to mu RT. Here we have taken 1 mole of gas, so mu is equal to 1. What is P? P is the pressure, V is the volume of the system, R is universal gas constant. So, R is always constant. Universal gas constant. Mu means the number of moles of gas. Here mu is equal to 1. For 1 mole of gas, mu is equal to 1. T is the temperature. T is the temperature, P is the pressure and V is the volume. Pressure, volume, temperature, they are the thermodynamic state variables. So, PV is equal to mu RT is the ideal gas equation. For the second process, we have taken P constant. So, pressure P is constant, P is constant, therefore, no need to write delta P. Delta indicates the change, pressure is constant, therefore, we have to write P into V. When pressure is constant, volume of the system changes. So, I write delta V. Delta V indicates the change in volume is equal to mu is equal to 1, no need to write R. It is always constant because it is universal gas constant. So, R. Delta T, temperature rises by 1 degree. So, change in temperature is delta T. So, P is the pressure which is constant, V is the volume. Under second process or at constant pressure, volume changes. So, delta V indicates the change in volume is equal to mu is 1 into R is constant, T is the rise in temperature. So, it is indicated by delta T. P into delta V divided by delta T is equal to R. P into delta V is equal to R into delta T. P into delta V by delta T is equal to R. Here we have Cp is equal to Cv plus P into delta V by delta T. This P into delta V by delta T is nothing but R. So, under constant pressure, so P into delta V by delta T at constant pressure, this is nothing but R. So, Cp is equal to Cv plus R. This is the relation between molar specific heat at constant pressure, molar specific heat at constant volume and universal gas constant. This equation can also be written as Cp minus Cv is equal to R. Cp minus Cv is equal to R. This equation is called Mayer's equation. This equation is called Mayer's equation. Mayer's equation, Cp minus Cv is equal to R. So, this is the relation between molar specific heats and the universal gas constant. Under constant volume, pressure changes, V remains constant. So, change in volume delta V is equal to 0. First law of thermodynamics, delta Q by delta T is equal to delta U by delta T plus P into delta V by delta T. Delta V is 0, so that whole term becomes 0. So, delta Q by delta T is equal to delta U by delta T plus 0. This delta Q by delta T is nothing but molar specific heat capacity at constant volume. So, Cv is equal to delta U by delta T. Delta U by delta T is the change in internal energy. For the second process, where the pressure is kept constant, if the pressure is constant, then the volume of the system changes. So, there is change in volume of the system, pressure remains constant. So, delta Q by delta T is equal to delta U by delta T plus P into delta V by delta T. Volume changes, only the pressure remains constant. So, the equation remains the same. Delta Q by delta T is nothing but Cp. Cp is equal to delta U by delta T is nothing but Cv plus P into delta V by delta T. So, P into delta V for an ideal gas equation is PV is equal to mu RT. P into, if the volume changes, then delta V is equal to R into delta T. P into delta V by delta T is equal to R. So, in that expression P into delta V by delta T is nothing but R. Cp is equal to Cv plus R. This is the Mayer's equation, or this is the relation between molar specific heat capacities and the universal gas constant. Take down. Here you have to write delta Q by delta T is equal to delta U by delta T plus delta W by delta T, dividing both sides by delta T. Now, we have the thermodynamic state variables. These thermodynamic state variables are of two types. First one is extensive variables. Extensive state variables and the intensive state variables. Extensive state variables and intensive state variables. What are extensive state variables? If the value of variable changes as the size of the system changes. If they depend on size of the system, then those variables are called as extensive state variables. If the state variables does not depend on size of the system, then those variables are called as intensive state variables. For example, consider a system. So, this is a system having molecules. If I cut the system into two parts, now total volume changes. So, volume of the system, when we cut this system into two parts, volume changes, right. So, volume changes, number of molecules or mass, it also changes, it becomes half. So, mass changes, volume, total volume is divided into 2. So, volume changes, total mass, it becomes exactly half. So, mass changes. So, volume and mass are the extensive state variables because they depend on size of the system. If a quantity depends on size of the system, then we can say that that quantity is extensive. If a quantity is independent of size of the system, for example, temperature. Temperature. Here in this case, for the first part, if the temperature is 20 degrees Celsius, for the second part also temperature remains the same, it is also 20 degrees Celsius. Temperature is same, it is independent of size of the system. So, temperature is intensive state variable. What happens to the pressure? Pressure is also same, initial and now the pressure is same. So, the pressure is also intensive. So, pressure, temperature, they are independent of size of the system. So, they are intensive state variables, whereas volume and mass, they depend on size of the system, therefore, they are called as extensive state variables. So, extensive state variables are volume, mass. As the mass changes, internal energy also changes. Therefore, internal energy is also extensive state variable. So, internal energy. Intensive state variables, temperature, pressure, etc. They are the intensive state variables and the extensive state variables. Ideal gas equation is PV is equal to mu RT. This is also very, very important for the examination point of view. Write, they may ask, write ideal gas equation and explain the terms. In that case, you have to write the expression PV is equal to mu RT and you have to explain it. What is P, what is V, what is mu, what is R and what is T.